electric dipole. It is a pair of point charges with equal magnitude and opposite in sign separated by a distance. Many physical systems, from molecules to TV antenna, can be described as electric dipoles. A water molecule is an example of an electric dipole. Even though the water molecule as such is neutral, the chemical bonds within the molecule causes displacement of charges. This displacement of charges creates a dipole with a negative charge on the oxygen end and a net positive charge on the hydrogen end. If water molecules were not electric dipoles, water would not have been a poor solvent. The field of an electric dipole. Electric field produced by a dipole is known as dipole field. Let Q and minus Q be equal and opposite point charges separated by a small distance 2L. The strength of an electric dipole is measured by a vector quantity known as electric dipole moment, which is the product of the charge and separation between the charges. Mathematically, it is represented as shown. The direction of P vector is always from negative to positive. The SI unit of dipole movement is coulomb meter. For points on axial line, the axial line of a dipole is the line passing through the positive and negative charges of the electric dipole. Consider a system of charges Q and minus Q separated by a distance 2a. Let P be any point on an axis where the field intensity is to be determined. Electric field at P comes out to be equal to 1 by 4 pi epsilon naught Q by Bp square, where Bp is R minus A and the direction of the electric field is along Bp. Similarly, electric field at P due to minus Q is 1 by 4 pi epsilon naught Q by R plus A whole square along PA. Therefore, net field at P is obtained by adding both the fields, and hence finally after simplifying we get the field at E as shown. Now replacing 2a Q by P and 1 by 4 pi epsilon naught by K, the equation gets reduced to EP equals 2 KPR divided by R square minus a square whole square, and its direction is along BP. As a special case, if twice A is much larger compared to R, then EP is reduced to 2 Kp by R cube. For points on equatorial line. An equatorial line of a dipole is the line perpendicular to the axial line and passing through a point midway between the charges. Consider a dipole consisting of Q and minus Q separated by a distance 2a. Consider a point P on the equatorial line. Then the value of electric field due to A is as shown, and the field due to B is also as shown. The resultant intensity is the vector sum of the intensities along PA and PB. EA and EB can be resolved into vertical and horizontal components. The vertical components of EA and EB cancel each other as they are equal and oppositely directed. It is the horizontal components which add up to get the resultant field. Now EA equals to EB. So E equals to 2EA cos theta. Now substituting the value of cos theta calculated from the diagram, we get the value of E as shown. Now again we put 2QA equals to P and 1 by 4 pi epsilon naught as K, so as to make the equation short. As a special case, if 2A is much larger compared to R, then E takes the value Kp by R cube and its direction is along Px. We also find that at very far off points, electricity intensity at an exile point is twice the electric intensity on the equatorial line. Physical significance of dipoles. In most molecules, the centers of positive charges and of negative charges lie at the same place. Therefore, their dipole moment is zero. CO2 and CH4 are of this type of molecules. However, they develop a dipole moment when an electric field is applied. But in some molecules, the center of negative charges and of positive charges do not coincide. Therefore, they have a permanent electric dipole moment, even in the absence of an electric field. Such molecules are called polar molecules. Water molecules, H2O, is an example of this type. Various materials give rise to interesting properties and important application in the presence or absence of electric field.